Good morning. It looks like I have 13 people, 14, so I'm going to give you guys a couple minutes to connect in. All right. You guys should be able to hear me now. Can you hear me? Can you hear me now? If not, let me know because I am not muted any longer. I want to go back to bed and forget school ever happened. What's that eating breakfast? Sounds odd. Okay. Hopefully Hopefully the audio will be okay for us. Otherwise, we will have to figure out a different plan. Continue to let me know if I get all weird again on my voice. I'm not talking like a robot, honest. I'm talking normally. Good morning, all. Hopefully you guys are all doing well, staying healthy, etc. Couple of housekeeping things again. Thank you to all of you who have turned in your homework, and I will get those things checked off, and I will kind of give you a progress report on how you've done in the last couple of tests and making sure that you guys get your homework in. This past week, you guys were asked to start on your projects that will be due in 2 weeks from today. I have decided, and I think we can do this, that we will do that class either through Zoom or Google Hangouts. That way you guys can share your screens and basically have your presentations. You'll just do it from your home. If you're doing a YouTube, you can still do it, show your screen, show the things that you guys worked on together. So details yet, whether we're gonna go Zoom or we're gonna go Google Hangouts. I personally, it's easier for me to do Google Hangouts because I have all your emails, but I'm not sure if you guys will be able to share your screens as easily as you can on Zoom. So anyway, hopefully that will work and hopefully the technology will be good for us. What we're going to do in today's class is we're going to go through the equilibrium chapter. We do have lab stuff set up that we're going to go through, and you guys will need to do a lab write-up for it. So be prepared for that. Again, like the last time we did a demonstration lab, it was like Chris and I were your partner doing all the work. You guys were still going to have to write it up. Hold on one second. Chris, you're making too much noise. You need to stop. Your breakfast is done. I'm sorry. You're going to have to wait. What was I saying? So anyway, we will do lab. We're going to first of all kind of talk through some of the things for the chapter itself. Hopefully you guys are doing okay with this material. I did send you guys a kind of an outline over the whole material for the chapter. That is on the Google Classroom link. If you want to have it to look at while we're going through things, you are welcome to do that. We are going to kind of go through this, but if not, you'll have this as a reference over the entire chapter of just kind of notes. I decided not to do it in a slide format because it's harder for me to share that screen. So anyway, I will kind of go through these things. Before we get started, do you guys have specific questions of things that you need for me to cover? Otherwise, we will cover everything. We might even have some time to go through some of the practice problems at the end of the chapter. From past experience, either people totally get equilibrium and it's easy, or it's challenging. So I want to see if we can give some tips, or if I can give some tips to understanding it. There is some memorization that you guys will just have to do to help you comprehend. Again, this sheet, going through it, if you're able to understand it, hopefully that will help you out as you move forward. Again, do you guys have any specific questions? I'm going to wait for any comments that I might get from you guys. All right, I'm going to assume no. If you do, I'm going to kind of check comments as I go throughout. So anyway, chemical equilibrium is basically understanding, and hopefully the video that you guys watched this morning is understanding that so far we've kind of talked about reactants and products. And we've always kind of talked about them going always in one direction. But now you guys are understanding that, guess what? It goes both ways. And the concept of equilibrium is you can have rates of equilibrium, but basically it's stable. Sometimes the rate of equilibrium is higher. Sometimes the rate of equilibrium is lower, depending on what's happening with the amount and the concentrations. But eventually, if there's no stresses added, it will kind of continue at a steady rate. Now, obviously, you guys, at this point, after reading through all of the chapter, are understanding that there are things that change and add stresses, whether it be a temperature change, a concentration change, a pressure change, that makes things change the rate of equilibrium. Also in this chapter, you guys were reintroduced to ionization stuff with acid and bases, as well as pH. So we're going to take a couple minutes and go through those things. So I'm going to kind of switch and kind of talk to you guys. I'm going to switch the camera again a little bit as we go through this sheet. All right, so hopefully you guys are understanding. We're going to kind of go through things again. All right, so chemical equilibrium, again, it's both the forward and the reverse reaction. There's some examples that we go through. And understanding. So solids and liquids are ignored, but yet aqueous solutions are not. So as you're kind of going through it, remember that this is the equation that you set up. Also remember, we haven't talked about equation sheets for a while. So this is an equation you could go ahead and add to your equation sheet. The sheet is upside down. Let me rotate. Now it's upside down for me, but as long as it's good for you. Going on. So anyway, this is an equation that you guys can add. The stoichiometric coefficients become the exponent. So as you're looking at a particular equation, knowing that if there's stoichiometry, again, that is the number in front of the actual molecule. That's the stoichiometric coefficient, and those become the exponent in going through. So the rules of equilibrium, there is an equilibrium constant, but sometimes things aren't running at that equilibrium constant. So then that's when you're going to have things weighted either to the products or the reactants. If eventually things will come to an equilibrium, but depending at the point at which you're looking at the reaction itself will depend upon whether you're at equilibrium, you're moving toward equilibrium, or you're moving away from equilibrium. So when I think about Ks, that is the equilibrium constant, where it's just running smoothly, that both the reactants and the products are there. However, if your K is small, I think about the K being like the fulcrum of a balance. like a teeter-totter. So if your K is small, okay, and you put that small end on a teeter-totter, it's going to go toward the left, which is toward the reactants. If you, again, the K is the equilibrium, but if you put the weight on the end of the teeter-totter, it's actually going to go toward the products. So again, with the double arrow, if it's actually at equilibrium itself, it will be shown as a double arrow. If it's weighted more toward the products or weighted more toward the reactants, then you can actually show the reaction as either that way toward the products or toward the reactants. If it's weighted one way or another, you would actually want to write that. Sometimes you need to rearrange it to write it showing that the reactants are always on the right side if it's weighted that way as well. So hopefully that makes sense to you guys. You did those on your own questions, etc. So sometimes if you're checking your answers, just to rearrange those. I wouldn't mark that wrong specifically, but just for the way that it's typically done, they rearrange those. All right, so what we're going to do is then going on to talk to Le Chatelier's principle, where he basically says, all right, if we add stresses, and those stresses can either be concentration, pressure, or temperature, anything that basically changes the steady state. Once it gets to that steady state, then it will actually shift so that a new equilibrium will be reached. And that new equilibrium, well, which way does it shift? Well, that depends on what actually has been changed. So looking at this I'm going to just move this sheet up again. Hopefully you guys can see this. If not, again, it is on your things. So the definition of, again, Le Chatelier's principle is when a stress such as a change in concentration, pressure, or temperature is applied to an equilibrium, then that reaction will shift in a way that relieves the stress and restores the equilibrium. It will have a new rate of equilibrium after it's restored. All right, so looking at concentration changes. All right, so there are several ways that we can actually change concentration. We can introduce new things, or we can remove things. But either way, that's going to change the concentration. If you increase the products, okay, believe it or not, when you have more things on the right side, it's actually going to then shift toward the left side. If you increase your reactants, it's going to increase and shift toward the products because you'll have more things that you can make. If you remove your products, okay, then you're going to have more of the other product and less of the reactants. If you remove some reactants, you're going to have more of the other reactants. So whatever you didn't actually remove, there's not equal amounts to actually cause that chemical reaction. So you're going to have basically some left over. If you remove a reactant or remove a product, basically that becomes the limiting reactant for the whole procedure, the whole reaction to occur. So if you remove a reactant or remove product, you're going to have more of the other one and less being made. All right. Pressure changes. Okay. So pressure changes. The important thing to remember about that, it has to do with the number of gas molecules, because solids and liquids, they actually don't change in their concentration just because the nature of those molecules themselves are already close enough packed that they just don't really change that much. However, the gases do. So when an equilibrium is subject to an increase in pressure, it shifts away from the side with the largest number of gas molecules. So you actually have to go in and when you're doing these problems, look and see how many molecules of gases there are in the reactants and how many there are in the products. And then you kind of have to figure out, all right, which has more. Then you look at the reaction itself as if the pressure decreases, the equilibrium will shift toward the side with the largest number of gas molecules. If it increases, then it actually is going to shift away from the side with the largest number of molecules. If there's no gases at all, guess what? Nothing's going to happen. Okay, I'm just going to check notes or check comments here as we're going through things. Okay, I hear that somebody is displeased with somebody disliked my thing. Who knows who else is on there, guys? This is a public feed, so who knows? All right, going on to temperature. And we're going to, once we kind of get through going through the details of this temperature stuff, we're actually going to do our lab for today. And Chris is going to be my lab assistant as we go through this. So the rules to remember. So again, delta H, if delta H is positive. So remember delta H is the change in enthalpy. So if it's a positive, it's going to be endothermic, and then the energy is a reactant. If it's negative, that means it's exothermic, giving off heat, and then the energy is going to be a product. So that's the first thing you need to determine. If it's positive or negative, if it's going to be a reactant, or if it's going to be a product, looking at that. When temperature is raised, then the equilibrium will shift away from the side where the energy is. If the temperature is lowered, the reaction will shift toward the side that's lowered. So again, looking at what happens when we're changing the temperature. So this is actually going to be our segue, because we're going to do the lab that deals with temperature. So I'm going to kind of remove these, switch the camera around again. And I just accidentally changed my filter. We're sepia toned. All right, so back to normal. Am I upside down?
Probably.
I'm going to switch this around. I'm going to assume that I'm upside down. All right. I look right side up to me, so hopefully I look right side up to you. All right, so if you guys will, go ahead and take out your labs, your lab books, your textbooks. Page 510 is where you guys need to be looking. And again, Chris is going to be my little lab assistant as we go through this. So I have all the equipment set up that we will need. Here, we've got the stove going with our cabbage water, which is boiling down way too much if I've been talking.
I need more water.
Well, we've definitely got cabbage water. All right. So setting this up, we're going to follow the procedure. I've already done step number 1, which is where I'm making my cabbage water. It's on the stove already. So number 3, we're going to put some ammonia solution into one of the cups, mark the cups. I did not dump my ammonia because if you guys recall, it's actually pretty strong smelling. So I'm going to go ahead and dump that into my cup here now that we're ready to go. I've put the vinegar right in front of the vinegar bottle, so you guys will be able to keep track of where we're at with that. So I will go ahead and dump some ammonia, even though I will not like the smell of it. All right, so I've already got my ice stuff set up. And I've got my water boiling in there too. All right, so Krista, do you want me to tell you what to do, or do you want to?
Yes, please. I didn't read the line.
All right, so we're going to go ahead and add some hot water to this beaker. We're going to keep it going though a little bit too, so we're going to keep it kind of. Just turn it way down. All right, so we've got hot water in our beaker here, kind of boiling water that we're setting up. So Krissa, would you go ahead and put about 20 drops of cabbage water into each of these? Yeah, go ahead. Into each of those.
Oh, there's one over here.
Yep. to each of our test tubes. No, actually, we just need two. We just have 2 extra in case.
12.
20 into each, please. Hey, Abigail, if you're set up to do the lab, do it along with us. That's awesome. I'm not necessarily anticipating you guys have all these things like cabbage water and purple cabbage on hand. So if you do, I think you're that much better for doing it. I'm kind of looking at comments now as Chris is filling the beaker, or excuse me, the test tube. So if you've got these stuff at home, go ahead and do it. If you don't, then you can just make observations on what we're going to do here during our time together. All right. So right now she has put about 20 drops of cabbage water into each of the test tubes. It doesn't seem like a lot, but that's okay because it's just an indicator. It's actually not going to play a part really in our reaction, except for it's going to sense what's happening, whether it's becoming more acid or more basic, which is what we're going to need to do. So Chris, into one of these test tubes, kind of following the procedure. It says rinse out the eyedropper. We're on step number 10, rinse out the eyedropper, or you can just use a different eyedropper if you want to. Add 15 drops of vinegar to each of the test tubes. So I've got plenty of eyedroppers, so just go ahead and do that. I think I have a bag of eyedroppers, don't I, somewhere? So 15 drops to each test tube. Is there another test tube? Or not a test tube, but refrigerated cylinder?
I don't know.
Eyedropper.
It smells.
All right. So you've done your 15 drops of vinegar to each. So swirling it should be pink. So that's where we're at in step number 12. Step number 13 now, use a different eyedropper to add ammonia to one of the test tubes. Add the ammonia drop by drop until basically it turns any shade of green. Do you guys remember what that is? That is basically a titration. So we're going to change it from the acid that it is, the pink color, to basically adding enough of the base, the ammonia, until it turns a green color. That's our titration. All right, so she's again adding base to get it to.
Tell me to count them because I forgot to.
No, it didn't say count them. We just want to kind of make sure that they're about the same shade of green once you swirl them in. So again, she's just titrating, adding base, step number 14 of our lab. All All right, so the reaction of this particular lab is, again, we're going to be changing some temperatures, but the actual reaction is NH3, which is ammonium, plus the vinegar, which is C2H4O2. At equilibrium, then it's making the ammonium instead of ammonia ion, cation, and then a negative anion. Now, this is an exothermic reaction, so that our energy then is going to be shown as a product. So real quickly, I'm going to kind of show you guys this. Can you see that? Okay. And we're going to discuss it in a little bit, what that reaction is. Like in my textbook, there is a typo. This is on page 512. It should be NH3 aqueous plus the vinegar makes NH4. So there is a bit of a typo in my textbook. Now, there are several different printings of textbooks, so you guys might have a different one. All right, so kind of going back to our lab, what we need to do next is she has added the ammonium to any shade of green. Then step number 15, place both test tubes in the ice water. So we're going to go ahead and I'm going to let you do that, Carissa. We're on now step 15. We're going to add that and allow them to sit in the ice water bath for at least 1 minute.
Do you want me to try from calling it?
No, because we're going to go back and forth.
Okay. It seriously smells like chicken.
That's the ammonia.
I know it is.
So just as long as it doesn't boil dry over there. Now, we didn't have a change in comparison of what's happening before and after, but we're sticking those in the ice bath. And then eventually we're going to do one each direction and then be able to compare. So we're going to let them basically both change together right now. I didn't set a timer, but we're going to give it another 30 seconds. I will set a timer for 30 seconds. Sometimes when we're waiting for time to go,
It smells so bad.
all right, so the next step that we need to do is we're going to compare them. We're going to pull them out and compare them. And then we're going to put one of them back in the ice water and then one into the boiling water. Okay, so we're going to be cautious on that. So our time has been our 30 seconds on my watch. So
It's a bit greener.
okay, so again, we're just kind of looking. We have decreased the temperature. Okay, now what we're going to do is we're going to put one of them back into the ice bath, and then one of them is actually going to go into the boiling water. Now, Chris, I do have this if you would like to hold it there because it will get a little bit hot, or you can just stick it in there as long as it's okay, doesn't tip over or whatever, we're good. So I'm going to go ahead and set my timer for 30 seconds. So the expectation is that the boiling water should be actually noticeably bluer than the one that is in the ice bath. Okay. Now, if you guys, and when you guys read through, so the blue color indicates more reactants, while the green color indicates more products. So which way are we shifting? Remembering that in this particular case, energy is considered a product versus a reactant. So if we're raising the temperature, we would shift it toward the reactants. If we're lowering the temperature, we're shifting toward the Did I say that wrong?
Mom, you put your timer on for 30 minutes.
So I did time. Let's go ahead and do that. I did put it on for 30 minutes versus 30 seconds. So now she's going to go ahead and compare. Okay. And it's definitely a different color.
Yep.
So, kind of show that with a white behind. Let's back it up so it's not dripping on my computer though. All right. So definitely now it's kind of changing even back a little bit more, but I don't know if you guys can notice. This is definitely bluer. This one is definitely greener. Okay. This is cold. This is the warm one. All right, so let's kind of follow through on our procedure again. All right, now it says put both test tubes back into the ice water. So let's go ice bath them again. We're now on step number 22 of our lab. So we're going to let them sit in there for a little bit again.
Should probably dry off the computer.
Yes, probably should. I'm correctly setting my thing to seconds, not minutes. I'll give it 45 more seconds there. So again, it is my expectation you will write up this lab and then submit it next week for our time together. So things that you're going to talk about is what's actually happening with the color changes and what that means, talking about if it's shifting toward the products, shifting toward the reactants. What's really helpful is there is an explanation of this on the page after your lab where it really talks about the color changes and what those means, if it's shifting toward the reactants or shifting toward the products. Okay. We're about timed it down again. So at this point, it is our expectation, okay, go ahead and Carissa pull those out, that they should be the same color again. Are they the same color?
Decently.
Yeah, swirl them and maybe stick them back in for just a little bit longer so that they are exactly the same color. They're close to the same color, but not exactly the same color. So we'll let them basically come to the same place again. And then essentially what we're going to do is we're going to stick one back into the hot boiling water again and leave one in the ice and just do another comparison and see if, again, those changes happen just the way we expect them to. All right, so again, one is going to go into the hot water bath and one is going to go into the ice bath. Okay. So I'm going to go ahead and set my timer again. Looking outside my window right now, it certainly does not seem like it is mid-April as the snow is coming down beautifully, but we have inches here in Lindenwood area. It is gorgeous though. All right, time. So go ahead and pull those out again. We'll do a comparison quickly. Oh, can you guys see those color changes?
Get closer to the camera.
You can actually here even zoom in a little bit on our camera. See those color changes? It's actually pretty good. Hopefully you guys can see those color changes. Indeed, this is the cold one and this is the warm one. So again, it's a bit more green with the cold and a bit more blue with the warm. All right, so
we're gonna unzoom.
We're gonna unzoom again. All right, so that basically concludes our lab. I'm going to mute for just a moment, guys, while we get things cleaned up. And then we're going to talk about this a little bit more, talk about the rest of the things with acid-base equilibria, something through the chapter. And then because we do have a bit of time, one-ended conversation goes a little bit more quickly. We are going to actually start on the practice problems together. That is Monday's homework. But just think, if we get through some of those, you'll be that much further ahead. So while I've got this muted, I want you guys to make sure, give you a minute or two, go get a sheet of paper or whatever so that we can start on the practice problems here together. And hopefully that will go a little bit better for you guys on Monday's homework. So I'm going to mute, and then I'll be back in a moment.
He's on Minecraft.
He is and he isn't. He's not online. All right, so it looks like I am unmuted, so hopefully you guys are back. Too bad, Brianna, you fell asleep. I'm glad you're back with us. Hopefully you're back with us. So anyway, this is kind of what was happening with our lab. Okay, so we had, again, ammonia with our vinegar. And when it basically, the reaction was occurring, we made ammonium, which is a cation. Again, a positive ion over here. Then we had basically a negative anion because the hydrogen left the vinegar, went into the ammonia. So notice how it's 3 versus 4. Again, there's a bit of a typo in my book as it changes. The energy is considered is exothermic, so it's considered a product. So what's happening then? If we decrease the temperature, we saw a shift toward the green and toward the products. If we increase the temperature, again, we put it in the boiling water, it shifted toward the blue and it shifted away or toward the reactants, away from where the energy is. So that's kind of the summary of what was happening in the lab. So kind of going back to our notes that we were taking, going through some different things. We just had some acid-base equilibria stuff. I'm going to zoom just a bit and maybe that'll be. Okay, so acid-base equilibria. So acids, again, are defined as any molecule that donates hydrogens, ions. Bases are defined as anything that accepts. That is not a new definition for you guys, but understanding what the acid ionization reaction is and what the constant is. So if you have a large K, you're actually, or K sub A, which is basically just our equilibrium constant, but it's basically showing you how weak or how strong of an acid it is based upon what that calculates out to be. It's just the same as you guys did the equilibrium constant earlier in the chapter. Now it's just used to determine basically how weak or how strong of an acid is. Obviously, if it's lower on the pH scale, it is a stronger acid, but it has the ability to break apart those hydrogens and those ammoniums more quickly. And so not all acids and bases are created equal. They're just not. They don't have the same ability to break things apart or not. So again, the larger the ionization constant, the stronger the acid is. So if the ionization constant is large, the acid is considered a strong acid. If it is not large, it's considered a weak acid. The larger, and again, vice versa for the base ionization constant. Again, if it's larger, it's a stronger base. If it's smaller, it is a weaker base. pH scale. So pH actually stands for potential hydrogen. And this should not be new information for you guys, but we will review quickly. So again, if it's between 0 and 1.9, it is considered strongly acidic. 2 and 6.9, weakly acidic. Okay. pH of 7, it exactly is neutral, but 7.1 all the way through 12 is weakly basic. 12.1 to 14 are strongly basic. So again, pH of 7 is neutral. So that is the basics of this. Now let's go ahead, and we have a couple of minutes, probably 20 minutes or so left in class. So let's utilize our time and go through some of these practice problems, and it will start you off well for Monday to get some of these things done. So take out your textbooks again. Hopefully you guys have done that. I'm going to kind of move my textbook here into field of view a little bit, so hopefully you guys can see both things. If not, hopefully you have your textbooks close by and are doing those. All right, so it says for the following reaction, the equilibrium concentrations are, and they list them, 0.25 molar. For the N2, it's 0.45 molar. For the H2, it's 0.63. Now, as you guys are remembering setting these up, we set this up with this equation. The concentrations of our reactants go on the bottom, and the concentrations of our products go on the top. Also recalling that the exponents are going to be any stoichiometric coefficients that we talked about. And in this particular case, they're all gases. So we're going to be able to plug in the concentrations for each of those. So we have N2 here, and we have H2 here. And that's going to be set up just like this. So now we have this set up. Now what we need to do is actually stick in our concentrations of these particular things. So let's go ahead and do so. So again, this is number 1. So setting this up. And that's going to be cubed, so that as we solve this particular equilibrium constant, can you let the dog out then? Mm-hmm. All right, setting this up, you guys should get 2.0 squared. In solving this, then, notice that we have to do things with the units. So we have 1 molality here. We're going to have 4 on the top, 2 on the bottom. So 4 and 2 giving you this as our units for this particular thing. Each of these has 2 significant figures, which means our answer has to have 2 significant figures, as this one does. Okay, so that means this is our equilibrium constant. So is this considered small, or is it considered big? Remember kind of the, like, what's considered big, what's considered small? Compare it to like 1. Is it much, much bigger than 1, or is it much, much smaller than 1? This is actually pretty comparable to 1, so it wouldn't be strongly weighted either direction. But when you're asked to figure out if it's weighted toward the reactants or weighted toward the products, typically it's either going to be pretty big or pretty small, not kind of big, kind of small. It's going to be definitely weighted one direction more than the other. But this is 2.0. It is weighted slightly, but it's not weighted very much. All right, go ahead and look at number 2. I'm going to give you guys a moment to read through number 2 before we start it. So I'm going to mute you for just literally a minute. I'm going to set my timer. I want you to look through the All right. So as I first read through this problem, I was like, oh my goodness, we have 10 grams and we have 2.2 grams of this, but yet our units for the gases are in molality. I'm like, oh, what are we going to have to do with this? But remember that solids and liquids really don't play a part in equilibriums. So these are both solids, so they're really not going to be figured in, calculated into our constants. So although they give us the actual mass of those, realize and remember that they don't play a part in the equilibrium constant itself. So we set this up again where we have our our products over our reactants. But again, this is going to cancel out. This one's going to cancel out because they're both solids. This is a solid. That's what that S means. This solid means, again, this cancels out, this cancels out. They don't play a part. They're not like canceling out that they actually aren't reacting, but they don't play a part in determining the rate of equilibrium because of the nature of a solid, a liquid, and a gas. Gases are more reactive because they occupy a larger volume. They're more interactive. They move around a lot quicker. So again, setting this up then, knowing that we can eliminate the gases, we have just the concentration of the NO2 and the oxygen diatomic. Okay. Again, the stoichiometric coefficients become the exponent. So this is 4. This is just to the first power, so we can eliminate it. Then we're going to put the concentrations in that they give us. Okay, that's just to the first power. Putting this in, remember your order of operations, you're going to actually do your exponent work first, then multiply your other components. You started out with 2 significant figures here, started out with 3 significant figures here, but because this only had 2, our answer then is only going to have 2 significant figures. And our units is m times m times m times m times m to the 5th power of m, just again, because of the way that this particular reaction went, there was nothing in our denominator to basically cancel out the units. So this. Now again, is this a small or is this a large K? Obviously, it's to the -5th. It's going to be a very small K. So which would it be weighted to? It would actually be weighted then toward the reactants versus weighted toward the products. It doesn't actually talk to us or ask us to determine that, but you can. All right, looking at number 3, I'm going to give you guys a minute again. I'm going to mute for a minute. I want you to look at the problem and see what we need to do, how we need to do it. And let's determine again if these equations for this particular next one can it be written as a single arrow, and how. So I'm going to mute you guys again for a moment, and I want you to look at number 3, please. All right, I'm back. Hopefully you guys. So the first thing that you're going to do is you're going to look and compare these numbers right here. This is to the negative fifth power. This is, again, close to 1, and this one is in the thousands. It's to the fourth power. So again, remember the rules. Think about the fulcrum. If I can kind of show you my arrow here. So the fulcrum is the K. If we have a negative, it's actually going to shift toward the reactants. If we have a really big number, think about the weight being on this end, it's going to shift toward the products, in case you guys can't see that really well. But understanding, so the first one, we have 2.2 times 10 to the negative fifth. That's a small number. So as you put that on, it's actually going to be weighted then toward the reactants. So when it's weighted toward the reactants, we actually probably want to rearrange that to show that so
Kidding me?
So I'm going to kind of do this. 2 and 0. Again, I should put my gases in here. All right, so that's letter A. Letter B, again, letter B is close to 1. So basically this double arrow, you can leave it as just as it is because it's close to 1. Again, it's not negative fifth exponent or to the fourth exponent as in the thousands. So again, it would be just as is with the double arrow. And then letter C then. Okay, so now we have a large. So because it's large, it's actually going to be shifted toward the products. So you can write it showing it shifted toward the products. Okay. Go ahead and I want you guys to look at number 4. And I'm going to mute again and see where we go. All right, so looking at number 4, again, the important thing to start with as we look at this is that solids and liquids don't play a part. We have a liquid as well as we have an aqueous. Aqueous we want to consider, but liquid we do not. Again, AQ meaning dissolved in water, but L stands for the liquid. So again, showing this and setting this up. Again, stoichiometric coefficients of 1 on each of these. So we don't, this is actually an easier problem, setting it up. So then we just stick in 2.3. And solving then, so 1.5. And this question is a little bit different in the fact that it's asking, so we calculated out, just realize that's kind of off the screen here. We calculated out what the equilibrium constant is, but they're saying, is this at equilibrium or is it not? So they give you the state at which it is at equilibrium, which is 2.3 times 10 to the fourth. That is where it's at equilibrium. So is it at equilibrium? Yes or no? Hopefully you realize that 1.5 is not 2.3 times 10 to the fourth. So we're actually going to need to then to shift toward the products in order for this to occur, or for it to reach. Okay, that's for number 4. All right, give you guys, I'm going to mute again, and I want you guys to go ahead and look at number 5. All right, so I'm looking at comments as you guys are working. Couple of questions that I need to answer, obviously. The 2.3, it looks probably like Tegan. It's either you or Evan is asking about the 2.3. That is simply an oops on my part. It should be 2.3 because that was what was given in the problem itself. I just wrote it wrong. My oops. All right, so plugging that in for each of those concentrations. Then there was another question about how do you tell if it's shifted toward the reactants or shifted toward the products? It is much smaller than it is. So it needs to shift toward the products to get larger. That's what it means. So looking and comparing, do you need to get it larger? Then it's going to shift toward the products. If you need to get it smaller, it's going to shift toward the reactants. It's no different than evaluating here and saying, is it shifted or do you need to shift it? It's the same kind of criteria. If you need it to get larger, it's going to shift toward the product. If you need it to get smaller, it's going to shift it toward the reactants. So kind of looking. The equilibrium, as you guys plug this in, okay, I oopsed in putting in the concentration right here. This should be 2.3. If you guys can't see that, I'm going to write it below. So we have 3.5 over 2.3. And again, those are the concentrations that are given in the equation for number 4. This is back to number 4. That's what's given. I oopsed and put the wrong thing. When you solve this, and just divide those two numbers, you end up with 1.5. Notice the units cancel out, so we don't have any units with this K. So this K equals simply 1.5, no units. But then the second part of the question asks, is it shifted toward the product or toward the reactant in order for it to attain equilibrium? The 1.5 is significantly smaller than the K, which is 2.3 times 10 to the fourth. That's given in our problem. So how do we get it to go toward that? We have to shift it toward the products. In order to get this K larger, okay, we have to shift it toward the products. Okay, does that answer the question? Hopefully so. Again, my oops on the 2.3. That was just misreading, miswriting, oops. And that 2.3 is different. The 2.3 times 10 to the fourth is the given K for it to be at equilibrium, versus the 2.3 is the actual concentration given in the problem itself. Just happens to be the same number, but remembering that 2.3 times 10 to the fourth, which is where K is at equilibrium, is that number, versus this is the concentration of 2.3 that we're plugging into our equation. Okay, going on then to number 5 at this point. Okay, number 5, hopefully you guys took a moment to look at that problem. If not, we're going to still do it because we're going to run out of time. So setting this up again, first of all, look, we have any liquids, any solids that we need to basically eliminate out of the problem. No, they're all going to be gases. So we're going to have to play, they're all going to play a part. So again, the SO3 is on the top, and that the stoichiometric coefficient is going to become its exponent. Okay, so then we can actually stick in what we need to stick in. For this, we're given concentrations for each of these. Now, part of this question asks, is it at equilibrium? If not, similar to number 4, if it's not at equilibrium, what do we need to shift? So given the concentrations, we're going to plug these things in. And I will try not to make a mistake in my writing them down. Okay. Remember, as you guys do this, order of operations makes a difference. So you have to do the exponents first, then you're going to divide and divide to actually solve. I'm going to kind of move this over a little bit. So again, do your exponent work first for order of operations. So solving this, all right, so we had 3 significant figures in each of these. So that means our answer has to have 3 significant figures according to our significant figure rules. Okay, units, what's happening with our units? So we have 2 and 2 molality and here, so we end up with 1 over m. So this, when we plug in the concentrations, is what we end up with. Now the second part of the question asks, is it at equilibrium or is it not? The equilibrium constant they give us is 4.41 over m. Okay, is that where we're at? Yes, it is. So it is at equilibrium. Okay, so we are set there for the problem itself. All right. We have actually no more time left. Do you guys want to continue or do you want to go on? Give me some feedback. All right. Kayla, I'm reading your note. Oh, we have a person that we don't know joining our class. Welcome. All right. I'm going to go ahead and since our time is up, I don't know what you guys have commitments for the rest of our time. Monday, it is scheduled for you guys to then continue to get all of your practice problems done before you guys have a test on Tuesday. If you have questions or needing a little bit of additional help, obviously just give me a call and I can help you work through it. But otherwise, I will go ahead and end our stream, our class time today. Continue to work on things. You do need to do a lab write-up for the lab that we did, our demonstration that we did in class. So please get those done and turned into me by this upcoming Friday. And we'll call it good. Have a good rest of your day. Enjoy the weather, the beautiful snow if you want to, or you can cringe about the snow. So anyway, see you guys later. And I'm going to sign off and I'm going to end our class time.